My name is Mark Weaver, and this presentation goes through the lightweight foam composite earth-covered magazine. My company, Karagozian Case, has been working with the Naval Ordnance Safety and Security Activity, a branch of NAVSEA, over the last few years to develop this concept. Karagozian Case, or K&C, was founded in 1945 as a structural engineering firm. In the 1970s, John Karagozian started working with the federal government in the nuclear silo test program. Since that time, K&C has been designing structures to withstand the effects of blast and impact loads. At this time, K&C has over 40 engineers and scientists that are located in Los Angeles and Sydney. At our headquarters building in Glendale, California, we have a DoD secret-level facility, as well as the KC Purple supercomputer, which has over 600 processors. Finally, in Pasadena, California, K&C has a prototype and testing center, which allows us to develop stress-strain data for a variety of novel materials. The background for this project is that nearly 75% of Navy magazines greater than 500 square foot in plan area are Arch magazines, as shown to the right on this slide, and they were built in the World War II era, and they're ready to be replaced. As you might expect, there have been significant advances in materials and analytical methods since these original magazines were constructed. It follows, therefore, that this effort is meant to leverage these advances to develop a novel earth-covered magazine design that incorporates lightweight and energy-absorbing material. The magazine should have similar or better blast fragment and forced entry resistance to that of the legacy earth-covered magazine designs. They should also be easy to maintain and upgrade. And finally, they should allow for construction timeline and cost efficiencies. The requirements for earth-covered magazines are summarized on this slide and can be broken into two categories. The first, structural performance requirements, consist of environmental loads such as dead, live, wind, seismic, and blast loads. Typically, blast loads will govern the design of any earth-covered magazine. To show that a structure complies with the stated blast load requirement, an analysis in accordance with UFC 334002 must be performed. At this time, FRP and plastic foam materials are outside the scope of the UFC. And as these materials are included in the lightweight foam composite concept, that means that an analytical methodology that can be approved by the Department of Defense Explosive Safety Board must be developed under this effort. In addition to the structural performance requirements, non-structural requirements defined in the DESER 6055.09 must be complied with as well. These requirements include fire protection, physical security, lightning protection, and environmental resilience. In addition, the design must consider operations and maintenance costs. The technology developed under this effort is referred to as the lightweight foam composite earth-covered magazine. It consists of fiber-reinforced polymer beams that are spaced at 2 to 3 feet on center that are resting on a rigid polyurethane foam bearing pad. The bearing pad is meant to absorb energy and also support the FRP beams. The materials, the FRP and the foam materials, were specifically selected to be durable, corrosion resistant, and fire retardant. Encapsulating the whole system, specifically for forced entry and lightning protection reasons, is a lightweight concrete topping with mild steel reinforcement. The concept works by leveraging the slight arch geometry of the FRP roof beam to resist a significant external blast load. As a blast load strikes the external surface of the LFC ECM roof, an arching force is imparted to the FRP beam, as shown with the blue arrow. This arching force is resisted at the bearing pad, first by the vertical leg, and then, as the beam is pushed downward, in the horizontal leg of the bearing pad. Both portions of the bearing pad are designed to crush prior to the FRP reaching its compressive strength. Thus, energy is absorbed through crushing of the foam bearing pad. The seal reinforcement in the topping is used for continuity and to tie the system together during large deformations. As shown on this slide, very simple calculations can be used to quantify the amount of energy that is dissipated through the bearing pad crushing. Key features of the LFC ECM are shown on this slide. First and foremost, the LFC ECM is meant to be modular, such that a bunch of roof panels can be constructed in the factory, stacked, and placed in a Connex box and shipped anywhere in the world. In addition, the installation process for the LFC ECM roof panels is meant to be very simple. All that is needed is to set the bent plate in the foam bearing seat, drop the panels onto the foam bearing seat, secure the anchor bolt at the foam bearing seat, and install side-lap connections between the various panels. Although originally designed as a single bay roof structure, this system can be easily modified to make multi-bay scenarios a reality. The status of the development of the LFC ECM is shown on this slide. At this point, we've developed an analytical model of the LFC ECM and verified that it's capable of capturing the static response of the LFC ECM's roof panels. The next step is to perform dynamic testing. This could be either blast testing or drop hammer testing in a lab setting to demonstrate that the analytical model is capable of reproducing the dynamic response of this system. Pending successful dynamic testing, we'll plan to do 100% drawings, specifications, and calculations that can be submitted to the Department of Defense Explosive Safety Board for approval. Although a timeline has not been decided yet for a full-scale blast demonstration test, speaking with DDSP to this point, we know that for the LFC ECM to be fielded, we will need to do a full-scale blast demonstration test of the system. As mentioned on the previous slide, approval by the DDSP is of utmost importance. If DDSP approves, the LFC ECM can be placed on the list of approved magazines, which opens up its use for a variety of owners and installers. However, it should be noted that the DDSP currently has no protocol for using high-fidelity physics-based calculations to support protective construction designs, nor protective construction guidelines for FRP and foam materials. Both of these elements are essential for the adoption of the LFC ECM and are the main reason why these activities play a central part in the current Phase 2 effort. However, following the Phase 2 effort, a full-scale blast demonstration test is going to be required, and this test will cost significant money as shown on this slide. Ideally, we'll be able to piggyback this test off other large-scale tests that are currently planned. But this is one of the things that we still need at this time is funders to help with this RDT&E cost. The key deliverable for the Phase 2 effort are the 100% drawings, specifications, and calculations for an LFC ECM, which will enable it to be listed on the list of approved ECMs, pending, of course, a full-scale blast demonstration test. KNC has been coordinating with various government and non-government stakeholders via conferences and trade shows concerning the LFC ECM concept and intends to do so for the foreseeable future. KNC manufacturing, which was recently established, will enable the LFC ECM roof panels to be made expeditiously and shipped anywhere in the world. And in fact, KCM assembled the half-scale panels during the Phase 2 effort. Finally, while the capital cost of an LFC ECM is expected to exceed that of the reinforced concrete options in the short term, various factors will help move that cost down in the long term, namely the life cycle cost benefits that are associated with the LFC ECM, the introduction of pultrusion tooling, and supply chain regularization after the COVID-19 pandemic. So why the LFC ECM? I'd say it breaks down into three main points. First of all, it's lightweight, and this lightweight will help reduce shipping costs and also the hazard produced by secondary debris deriving from an LFC ECM. Second, superior O&M. The LFC ECM is constructed totally of corrosion-resistant materials, and that can be employed in harsh environments. Additionally, its modular nature allows for rapid installation and easy replacement, and also its connections do not require welding. Finally, energy absorption through the slight arch and the energy absorbing bearing pad makes for a very efficient system from a structural performance perspective while still meeting the blast resistance requirements of earth-covered magazines.